This is eVTOL testing and analysis solutions for certification. So there was a team of us having a meeting one day, and we discovered we have quite a few solutions within this new trending electric vertical takeoff and landing space. So we wanted to put together just a little overview of some of the applications we think are very interesting. For those of you who don't know, HBK, Hottinger Berlin Care, is a testing conglomerate made up of simulation, software, sensors, and data acquisition, covering a wide range of applications. So we think this is a very cool environment. We see a lot of multi-physics overlapping phenomena that need to be tested and analyzed for certification. So a brief overview of the agenda. We're going to go over the eVTOL current engineering landscape. We're going to look at performance of the electrical systems and really how these new propulsion systems are kind of setting us back to some old problems. One of which is that they're creating noise, they're creating vibration. We have new structures. We have these propulsion systems that are relying on old methods like propellers, which are creating noise and vibration. And this becomes a serious certification and public acceptance issue. And then lastly, we have this electrical system that's causing this sound, this vibration. We need to understand how to execute these aircraft reliably. We need to understand how to model their durability. We need to understand how to accelerate, understand, characterize this durability. And this is through things like lightweighting. This is through things like increasing strength, so we can really get these aircraft in the sky. And then we'll naturally have the Q&A. So HBK, who is Hottinger, Brule, and Care? Well, HBK has a lot of applications, as I mentioned. There's probably more than this, but kind of the 9 areas we key in on are this power quality for fault testing, electric powertrain development. This is those new electric flight motors, structural durability and fatigue, acoustics. These things are going to be flying over our heads. Electric is quiet, but it is not in absence of being annoying. Propulsion testing for production. So how do we make sure that these things are airworthy? Ground vibration testing, analyzing those structures, making sure that we're not going to hit any vibration modes. In-vehicle sensors for monitoring things like vibration. Reliability and maintainability, you're going to hear a lot about that. And also flight controller validation. Today, we're going to zoom in on the story of electric powertrain development, structural durability and fatigue, and then reliability and maintenance, because those kind of tell a continuous trend. So HBK as a whole, as I mentioned at the top, our product or God or whoever makes some physical phenomena. This is where HBK comes in. We have sensors that can measure that phenomena. We have data acquisition, which can record those sensors that are measuring that phenomena. We create data, create lots of really good, really accurate data. We have software tools for analysis, and then we have some experts, and we have the software tools that can turn this data from those sensors into actionable answers. In this example, predicted time to failure. And then with these answers from that analysis, from that data, from those sensors, you all as engineers can start to do that product improvement. So really, we try to take care of this middle. We try to make it easy. We try to make it accurate and trustworthy. So that's HBK. And we do that in a wide variety of areas: sound, vibration, strain gauges, torque meters, current sensors, voltage measurements, the list goes on. And the real goal of HBK, if we have to look at it a million miles high, we want to go from design, finite element models that I think I can, to the really, it is a physical item. We are making sure that this is safe, that this is airworthy. I know I can. So we really want to give data, give accurate data, give dirty data, or give clean data, that we can transition into really trustworthy products. So the current landscape of the electric vertical takeoff and landing aircraft. So these new aircraft, they're new structures, things that we have not really flown before, or structural movements that we haven't really had experience with. New propulsion systems that have their own challenges. We think the weight of batteries, the structural rigidity we need in different areas because of the structure, different vibrations, things that are coming from the motors. And because we have this limited energy storage, we go back to things like propellers. And now we've largely gone away from propellers because they have a lot of issues with things like structural vibration. And Doug will speak much more about that. But they're bringing these historic challenges back to life. In addition to all these new problems we have with distributed propulsion and batteries and new structures, we have some of these old problems as well. So we have all these vibrations, we have all these things that have been engineered out of most aircraft, but now we have an electrical system causing a vibration. And we almost need to start re-engineering the wheel so that we can certify, so that we can safely get in these aircraft and be confident when we're flying. And the fortunate thing is HBK has solutions to help measure these things so you can understand them, so you can identify single point failures, so you can identify risks, and so that you can start to solve these challenges to get these aircraft in the sky. So what are the eVTOL engineering challenges? Well, can these things even fly? There's hundreds of companies with dozens of different geometries, topologies. Are they going to fly? What happens when they fly? When we do get them in the air? I mean, where are they going to take off and land from? What is that going to sound like when it's going overhead? How are we going to deal with charging infrastructure? There's so many questions that start when they start flying. Do we need to have higher safety requirements because of the number of flights going on? And what does qualification mean? When we look at the FAA regulations, which are actually very quickly evolving in this space, what does it mean to have a certification and qualification? So these are a lot of the questions that we're getting asked by customers when it comes to measurement. Now, one of the key enablers, and this is a theme that'll kind of perk up in all of our conversations, is a design FMEA. And this is really at the highest level, us making a decision tree for where to spend time and money in our design. And from the electrical side, my area of expertise, I look at this as a lot of single point failures. But Kurt, I think my colleague Kurt will have some more words to say about this.
Yeah, thanks, Mitch. Yeah, so look at it this way, right? It's kind of brave new world out there with eVTOL. Lots of let's say underdefined design space, right? So we have a lot of design flexibility in front of us. Not a lot of history to look back on, but a lot of new design flexibility to look forward to. With that comes the need for what we call design failure mode and effects analysis. So recognize what failure modes are, identify functions of the aircraft or systems within the aircraft, and not just their functions, but also how these pieces interact. Mitch, can you go ahead one here, please?
Oh, of course.
Yep, thanks. And really what we're trying to do with a failure mode and effects analysis is to recognize what are the possible failures that could happen and how prevalent are those failures, how risky are those failures, what kind of an impact do those failures have, what kind of control plans can we put in place to guard against or to recognize these failures. And ultimately what we're trying to do is develop action to mitigate the highest risk causes, right? So new design space, exciting, kind of scary at the same time. Let's recognize possible failure modes, how they influence our product, and then prioritize around the failure modes that are maybe the most risky or most prevalent or most safety critical. One more advance, if you could please, Mitch.
Oh.
So really with FME, what we're trying to do is upfront is say, how do we design reliability into our product? New design space is cool. We just need to make sure that we're focusing on the right parts of that design. So, we don't have infinite time or budget. So how do we prioritize? Well, let's prioritize around failure modes that really influence reliability or user experience or safety or whatever. Okay. So let's use this as a tool to map out where we are in this new design space and prioritize accordingly. Thanks, Mitch.
Excellent. Thank you, Kurt. So now, once we've started looking at that design space and making sure that these things are more reliable, we need to start digging into the details. So I'm going to take a moment and speak on maximizing electrical performance. So the quick pitch, HBK has a power analyzer solution along with current sensors, load cells, torque sensors for analyzing electric motors. So this is measuring voltages, currents, accurately measuring power, and recording data for understanding what's happening in these motors and inverters. We do 5 things well. We measure electric and mechanical systems, so you can understand that battery to propeller. We make very fast and accurate efficiency measurements, so you can understand energy consumption through a flight cycle. We can go to many channel counts. So if you have many motors or you have high phase counts for those redundancy purposes, we can measure all of those channels in one place. We record lots and lots of data, and we have real-time feedback and equations for things like hardware in the loop. And we do have local support and training, and people have had a lot of experience measuring these motors. Historically, HBK has been involved with aircraft electrical systems for quite a long time. We've been working with DO-160 type power quality measurements for many years, where we actually make measurements throughout the full body of the aircraft, looking at the APUs, the different power distribution points. And this really goes up to hundreds of channels, making measurements for a full flight sequence so we can understand what are the different fault areas. Is this aircraft going to be safe electrically? So we have a long history in this aircraft electrical network testing, which has really gone very nicely into this eVTOL space. So we've really been able to grow up with electrical systems in aircrafts. So we've gone from this hundreds of channels in a full body aircraft, where we might have distribution of measurements throughout different areas of the aircraft, separated by very long distances. We can daisy chain our measurement systems together to take hundreds and hundreds of channels that can all be recorded and viewed in a common location. And this allows us to really trust the actual aircraft. You know, we can have miles of cable throughout this aircraft, and we can measure all these different points to get that full understanding, to start to identify, can I trust what's happening in my FMEA? Can I identify new things that need to go into this failure fault tree? If something happens in the sky, how do I predict it in the future? So we can start to make all these measurements and really understand this system in depth. Now that's traditional aircraft, but a lot of the same principles apply. Now, if we look at these eVTOL, we're adding in a lot of motors. And if we really want to understand this new novel aircraft space, we have to look at it a little more closely. So we have these inverters. They're taking a battery and they're switching at a really high frequency. You know, we're seeing 10 to 30 kilohertz, but some people are going much higher. So this high frequency inverter with these switches turning on and off in a clever pattern, put this high frequency voltage at a motor. This motor turns this voltage and current into torque and speed. And we find we get, you know, fundamentals of current that are somewhere in the 0 to 2 kilohertz range. So we have these already 2 frequencies. We have this high frequency of switching. We have this, you know, low to medium frequency of electrical excitation. And then this gets transferred into torque and speed, which is, again, a third frequency of interest that's somewhere in the 0 to maybe 10K range, depending on the aircraft and the gearbox type. This is then making its way to torque and speed at an output shaft, and we're seeing torsional vibrations. We're trying to lightweight these motors. We're allowing for more vibration to come in. And what we find is that this inverter is a controllable computer. We can program this. We can change its switching pattern, which this means we have access to controlling things like how my inverter affects structures. We can make software changes to affect things like mechanical vibrations, mechanical structures. So this leads into an opportunity. You know, we have this unknown space where we can tune an electrical thing to control a mechanical output. And this is where you really do need to understand voltage, current, torque, and vibration to understand the system level and what might be transferring to things like structures. Now, new propulsion technology introduces new problems, and these are mostly electrical problems, but we'll see how they bleed into things like structures. So we have many motors. So we're seeing many motors. Again, this is to avoid things like those single point failures that Kurt referenced. We're seeing increases in voltages. We're seeing these inverter driven, these really high frequency electrical signals. These have high phase count and high complexity, again, for that redundancy. And we see electrical networks where we might have multiple motors, multiple inverters, actuators, and the vehicle power grid all coming off of a battery. All of these things have frequency content, which is going to get pushed onto that battery. And we have to ask ourselves, how much frequency, how much content can a battery survive? Is it safe? In terms of integration, we're lightweighting motors, which means low inductance, which means current ripple, which means torque ripple or torsional vibrations. So we have decisions to be made with how we control that inverter based on these lightweight motors. Torsional vibrations from the motor and currents can cause bending moments in propellers or whirl flutter, which I think we'll hear about a little later. All of these networks applying to one battery create a high stress DC network. And it all ends up in really the same problem we had with the electric or aircraft electrical networks traditionally, is we need to make sure the power quality is good enough that we can safely fly these vehicles. So it all comes back to power quality. We just have a lot more points of measurement now and a lot higher frequencies. So, in a measurement of an electric powertrain, we're going to measure the battery, the inverter output, the torque and speed, maybe vibration, maybe microphones, potentially CAN bus or IDDS. And with the HBK measurement system, we can measure that all in one place and show you that as a visualization. So some of the tests we're seeing in the performance space are really looking at that motor and characterizing that motor and inverter for efficiency, for fault tolerance, for power quality. And what HBK offers is extremely high accuracy, the ability to bring in temperature, battery, look at the motor control. So you can understand that kind of soup to nuts, that full battery to propeller operation, because fault tolerance is so important. Designing these controllers for fault tolerance is so important. We need to understand these failure modes. We can look at the mechanical performance, the thermal, the vibration. Do these things overheat? Do they put out too much vibration? We can help with that fault analysis by recording lots of data. And then for the motor control nerds who might be tuning things to reduce noise, to reduce vibration, we can look at the DQ0, the torque ripple, harmonics, power quality, do things like efficiency mapping. So we have a really nice package for doing that motor analysis. One of the additional benefits that we have is we use an algorithm called cycle detect, where we can actually track the fundamental frequency as speed is changing, which means if you are executing a flight sequence, as your motor's speeding up, we can give you a really good power measurement. As you're going through that flight sequence, we can give you a really excellent power measurement. You can see your power, your reactive power as a trace, so you can really understand how that machine is consuming energy, where it's less efficient, where we can optimize efficiency, where we might need to overpower, where we're overshooting. So we can start to help you analyze these flight cycles for faults, for efficiency, for energy consumption. So this is really cool stuff, and this is pretty unique to HBK that we can offer this. Now this leads into one of the really interesting things is doing a full vehicle electrical analysis, more of that traditional power quality testing. And what we find is safety is critical. There's many of these configurations, and we have a lot of different fault conditions we need to go through for certification. Loss of motor, transition states, weather conditions. And fault conditions are difficult and dangerous and hard to repeat during flight testing. There's a company in the UK that crashed one of their prototype vehicles because they were physically testing some of these fault conditions. And how do you repeat wind conditions? How do you repeat a bird strike? How do you safely repeat loss of motor? And propeller tests are the traditional iron bird. You get prop wash without a very expensive wind tunnel. It's difficult. So what we're seeing is many of our customers are going towards mapping their powertrain with dynamometers. They'll have a flight simulation computer where they're telling dynamometers how to act as propellers for the 8 different motors. They'll really accurately simulate these different fault conditions with a vehicle model, and they'll have their real motor controller, their real inverter powering multiple motors, so they can actually test all of these fault conditions with the real battery, with the real motors, and look at this eVTOL performance through a flight cycle to understand if they're stressing that DC network. And the dynamometers can accurately simulate the propeller dynamics. We can really repeatably simulate these different fault conditions. It's safe. We're starting to see it get used for certification, and you're avoiding those prop wash or expensive wind tunnels. Now, where HBK can help with this is we have flight simulators through our concurrent real-time platform. We have high channel count power analyzers where we can measure the electrical signals and the torque and speed. For each one of those motors, we could take all 6 or all 8 at one time, record all of that data in one place, have all of that data for a full flight sequence, and we really give you that ability to operate hardware in the loop because we do things real time. We can certify with that data, and we really simplify that test system. And again, you have the highest accuracy. You have that long history of doing these electrical tests. So this is really exciting, and I think this leads into understanding how does the electrical system affect the vehicle? How do we identify those single points of failure? And this is where I'm going to lead into handing off to my colleague, Doug. But Doug, I have a question for you. And, these electrical things are creating things like torsional vibrations. Does that couple to structures? Do we actually have to worry about that?
Oh, you definitely have to worry about it. And hopefully with the slides I have here, I will help you better understand how the torsional vibration, the different types of excitation that are now getting bolted on these low-flying electrical aircraft. So here's roughly the some bullet items I want to cover from a noise and vibration standpoint. These challenges are sort of, I feel like, the top 2. One, these aircraft have to get certified, either by the FAA or by EASA. But they also have to pass the public acceptance test, which may even be a bigger hurdle than the certification. So let's talk a little bit about certification from a FAA standpoint. First, some of these things are well defined from a certification standpoint. One of those areas is flutter. So there's 2 different types of flutter. There's classical flutter, which is basically an instability due to the interaction between aerodynamics, inertial, and elastic forces. But then whirl flutter. And whirl flutter is sort of a new beast in a way that used to be an old problem, and we got away from because we went to the jet engine, the turbine, instead of a propeller. Well, these eVTOL aircraft have adopted the propeller because that is the most efficient way to get the aircraft off the ground at low RPM. Well, now that you have reintroduced the propeller, now you have to deal with whirl flutter, where whirl flutter is basically the stiffness of the housing of where the motor is bolted onto the wing or the different parts of the aircraft, and the excitation of that RPM of the propeller. So that's a little bit about flutter. So we took the HBK's BK Connect, and we took some time data, as you see on the left-hand side here, and processed it. Took a little bit closer look at it in the time domain, but then post-processed it into the frequency domain, which is what you see on the right-hand side here, and did some modal analysis on a small drone. So if you take a closer look at the, I'll call it the electrical data, the torque, the current, the voltage, the speed. If you zoom in and take a closer look, you can see that the torque has got not only a static value to it, but it's got a dynamic riding on top of that static, which if you think of it, that motor is sitting there oscillating back and forth. Well, if you take a closer look in the frequency domain, that shows up in this example of this data that we took at roughly a little over 8 hertz. It's like, all right, who cares? You're probably not going to hear it. You probably are not going to necessarily feel it. But just so happens that if you look at it from a modal analysis standpoint or a ground vibration test, GVT, that drone had the first wing bending was at 8.9 hertz. Then the lateral fuselage bending was at 9.2, and the vertical fuselage bending was at 17.4. So taking the tools that HBK has, not only from a software hardware standpoint, but also from a transducer standpoint, we did a modal analysis on this drone to see where these bending modes were. And with Flutter, basically, if you set right on top of one of these modes, the wings could basically fatigue and fall off. And my colleague Kurt will talk a little bit more about that after I'm done here. But that's why it is such a critical issue. And the FAA regulates this, that each aircraft has to be tested part of, I think it's CFR 14, part 25 certification. So they have to go through this type of analysis, where we have progressed to the point where most aircraft either had 2 jet engines on it or maybe 4, 2 on each wing. Well, look what we've done. We've taken aircraft now and we're putting multiple propulsors on the wings, which are running at speeds that are right in the structural frequency ranges of these aircraft. So it's also from a safety standpoint. So I talked a little bit about Flutter and sort of the structural part of it, but there's also the noise emission and safety. Now, safety is blended throughout this whole process. So let's look at noise emission a little bit. So currently, aircraft, the engines have to go through what's called SECT, Static Engine Certification Test. And as you can see, basically putting a jet engine on a test stand and then putting microphones all around it. Now, HBK's Tessia solution helps to quantify that data, to analyze it in the time and frequency domain. But you also have flyover certification. Here's where we start getting into a little bit of a gray area. By that, I mean the FAA has standards from an acoustic standpoint. Can't be over a certain dB level, setting on the runway, and can't be over a certain dB level when it's flying over your head during landing, during takeoff. Those are clearly defined. Well, from these new electric vertical takeoff and landing aircraft, the actual dB level is very low compared to these jet engines. So The certification currently is not accurate for these types of vehicles. And the FAA is currently working on it to try to come out with new certification rules and regulations, but that hasn't been done yet, especially since these aircraft are not necessarily from a traditional design, meaning they got multiple motors, they got some vertical motors, they got motors that tilt for takeoff and then tilt the other direction to move forward. So you can look at it many different ways. What I wanted to point out here is HBK has got several solutions, from an acoustic standpoint. You can do wind tunnel testing. You can have an acoustic array on the ground and fly the aircraft over and do beamforming or use the acoustic camera. Because just because it makes noise doesn't necessarily mean you don't have to figure out where the noise is coming from. So these different tools can help you better understand your aircraft and where the acoustic excitation is coming from. So now let's focus a little bit on the public acceptance. And the reason I said that this could be even a more critical thing is that no matter how safe it is, no matter what it sounds like, if it's not accepted by the public, then a lot of these startup companies are just not going to succeed. I mean, a lot of their business model are air taxis. So it's not only for delivery type things. Now you're going to be getting in them and flying from point A to point B because it's faster, more economical. But if the public doesn't like how it sounds or does not feel that it's safe, then they don't have to use them. So from a sound quality standpoint, I pointed out some things from an exterior standpoint, but now the interior. Obviously, the interior on these, using them for air taxis, it has to be relatively quiet. So you get into sound quality, not only from an interior standpoint, but from an exterior standpoint. And that's why I made the comment here, swarm of bees. So maybe the dB level is not very high, but what does it sound like? And some people may say it's like, oh, well, it could be perfectly quiet. Well, does the public want perfectly quiet? It's really nice for me to be outside and I can hear a helicopter coming from a long distance. So I know it's there. These eVTOL have to be quieter than a helicopter, but I still think they need to have some type of acoustic signature to it so we know they're here, because they are going to be flying very low level, and the quantity of them is going to be a lot greater than what we're used to. The other item I state there, does the sound make you feel safe? So if you look at like the interior cabin noise, how do you want the sound to make you feel when you get in one of these eVTOLs from an air taxi standpoint? If you shut the door and it gives us a rattling sound that doesn't give you confidence that you just climbed into something very, safe, then you're probably not going to want to take the second ride. So HBK has numerous tools to look at airframe, look at transmission loss, look at the noise field for interior, static engine, flight test, exterior, look at quality control, look at your cabin noise. This was a very quick overview from a noise and vibration standpoint, but it doesn't end there. Now, Kurt, I think you have some information and can discuss more from a durability, reliability standpoint, because they are going to be flying fleets of these aircraft. So they have to have some way to manage the fleet and make sure it's reliable and safe.
Yeah, thanks for
Over
that,
to you,
Doug.
Kurt.
Thanks, Doug. Yeah, so Mitch, I think, hit on a key phrase at the start of the day today. That was multi-physics. Think about all the physics that's involved. We got electrical phenomena, we got mechanical phenomena, we got fluids, we got all kinds of things going on. So, electrical phenomena like torque ripple becomes, if we're not careful, it lines up with structural resonance, like Doug talked about. Structural resonance leads to durability problems and strength problems, whatnot. So what I want to look at now is just briefly look at the challenges related to durability and reliability in the eVTOL world, and hopefully point out some solutions along the way as well. So how do we improve durability and reliability of an eVTOL aircraft or a fleet of them? So the way we need to look at this is, challenge one is strength and durability. How do we make sure these things are strong enough to fly and durable enough to continue to fly? And it's not just a question for traditional airframe guys. This is not just an airframe question. This is really a question for all kinds of things in the aircraft. The battery system, the heat exchangers that go with the battery system, landing gear. Some of these are new to eVTOL. Some of these are old components, old structural components. Landing gear have been around for a long time. But just the same, we have to be able to understand their strength and their durability so that we have a solution that will continue to work over time. So how do we approach this question of durability and reliability, or strength to begin with, for example, strength and durability? Now we have a lot of CAE-based simulation tools at our hand, available to us to use here. So the question is, how do we balance out simulation, say structural durability simulation, and physical testing? A good friend of mine, brilliant engineer, said, let's predict what we know the physics about, and let's test where we don't. Let's test to verify. So really, we look at this in two ways. These days, an engineer can approach this question of strength and durability. First off, is let's model what we know. In other words, if we can describe the physics, of how this thing resists, say, dynamic loading or torque ripple or flight maneuvers or whatever, if we can understand that physics, then we can use CAE tools like finite element modeling and fatigue life prediction and such early in the design stage, so we can design durability into our parts, right? So we can quickly assess durability and strength and such, which means then we can build durability and strength into our structure. So when we do get to testing, right, we have to do verification tests. We know this. When we do get to testing, we have an increased chance of success, right? So we're trying to improve the confidence of success, because there's nothing that's going to take more time or money than finding out that a product we've prototyped and we test fails, right? That's what we don't want to have happen, the build it, break it, fix it loop. We want to build durability and strength into our parts as early as possible as we can using virtual tools. Right, so an example of this virtual, let's model what we know, or where the physics is understandable. Let's use numeric simulation to help us. Here's an example of that. This is an example of predicting the durability or the fatigue life of this structural part. Okay, so we start this. This is finite element analysis up here. So how does this structure resist load, whether that's dynamic load or static load or thermal or whatever it is? FEA, finite element analysis, can help us understand how loads become stress. But nowhere in a design spec is the line that says keep the stress below 600 megapascals. The spec will say something more like it has to last 25,000 flight hours. So then we need to start thinking about bringing in fatigue loading. So get from strength into fatigue life. So we're doing this virtually, right? We'll rely on testing later for verification purposes and also for correlation purposes. But if we bring this known physics of failure, this fatigue concept, this fatigue failure mode, if we bring this early into the design process, we can iterate on this design very quickly and make sure that we optimize the product for strength and for durability. Okay, because the next challenge around the corner, once we have one of these things flying, the next challenge is lightweighting. Okay, so through grace of God or through some stroke of luck or whatever it is, we have an eVTOL aircraft prototype that flies. That's awesome. Okay. So the cool thing is now we understand its performance environment. We understand its vibration. We understand the mission, in-service loading and such. But we need to now think about how do we improve performance, reduce weight to improve range, for example. Okay. So this lightweighting challenge of design B, next design revision, how do we optimize its strength and durability? How do we optimize its performance without impacting strength, without sacrificing durability? Okay. So we want to bring this durability analysis into the redesign loop so that we can effectively lightweight. And we're going to look at how we could use this tool called ENCODE from HBK, fatigue analysis software, to help us with this redesign loop. Okay. So like we said before, we're going to model what we know. If you understand the physics, we're going to try to bring the modeling of that physical behavior, that durability, that strength, that stiffness, whatever it is, try to bring that as early into the design process as we can using computer simulation. And the physics that we don't understand, we'll test. And also even the physics we do understand, we'll test to verify at the end. Okay. Which then raises the next big challenge, which is how do we durability test these aircraft? Okay, really complicated loading, really complicated vibration. As Doug and Mitch both said, one of the challenges with eVTOL is that for a variety of reasons, they're typically prop driven, and returning to props has brought up some engineering problems that the aerospace world has faced in the past, but has kind of grown out of through the godsend of the turbine engine. Here in this case, now we have a prop engine. We have a prop based, which creates really complicated loading. So how do we do structural durability and strength testing in this environment? Validation procedure is going to be this. Let's measure or predict in-service loading, right? There are ways we can measure using HBK sensors and DAC, the kind of stuff that Mitch talked about earlier. There are all kinds of ways these days to numerically simulate aerodynamic loading to predict loads and such. But either way, we need to understand what's the operating environment in terms of load, pressure, strain, these kinds of things, right? And then we can reproduce those conditions in the test lab, and we can accelerate the way we do that such that we can look at assessing, say, a 10-year life of the aircraft without testing for 10 years. Okay, so we can accelerate that testing loop. Realistically, what these tests look like is kind of what you're seeing here. Lots of servo hydraulic actuators that are used to replicate, say, the aerodynamic loading or vibration loading on different parts of the airframe. We're looking at an airframe test here. We'll talk about component level, smaller stuff in just a minute, which is important because these days, we have batteries that are subjected to vibration. We don't want that to fail. We have inverters, we have heat exchangers, we have all this stuff, eVTOL specific stuff that we now need to think about the durability of, not just the airframe. This type of full scale or even smaller scale testing, could be done in a static way, right? Static testing, how strong is this wing in a static sense, right? Or it could be done in a fatigue testing, durability testing, where we have repeated blocks of cyclic loading over and over. HBK has just a ton of solutions to help in this environment. Sensors, load cells, strain gauges, accelerometers, data acquisition hardware, all kinds of solutions to help with this, including software to analyze and track trend during durability testing, how our loads or strains changing. Hopefully the loads input aren't changing. That should be a part of the controlled test loop, but resulting strains, we can use that then as an indicator of structural health and help us understand how the test article itself is behaving as the cyclic loading continues. So that's kind of airframe testing. That's big stuff. Let's look at smaller stuff, because at some point you're going to be faced with the challenge of how do we know the battery tray is not going to fall out? How do we know that the heat exchanger that keeps the batteries cool isn't going to leak, isn't going to break? Okay, the way we do that these days, we often use like a vibration electrodynamic kind of a shaker rig like this, where this is capable of moving this table back and forth, right, and reproducing the vibration environment that the aircraft feels, but we can reproduce this now in the controlled environment in the lab. Okay, so these test rigs are awesome. HBK makes some of these under the LDS name. But the question is, what shaker profile? and for how long, right? So these shaker tables do an awesome job of reproducing vibration. Now, should that be reproducing PSD random vibration, swept sign vibration, a combination of the two, sign on random, swept sign on random? There's even random on random now, like two narrow bands of random together. And how long, right? How long? So we're going to look now at ways we can use this we call ENCODE software to take measured vibration data and convert it into what we call an equivalent damage accelerated shaker profile. And that may be a random PSD, it may be swept sign, sign on random, swept sign on random, lots of different ways we can do this. The key is this is potentially thousands of hours of vibration being collapsed down to maybe tens or hundreds of hours in the test lab, so we can run this shaker and reproduce the vibration environment of thousands of flight hours in tens or hundreds of lab hours. Now you may say, hey, wait, hang on a second. This really isn't that hard. This shouldn't be that hard because there's all kinds of different specs for shaker profiles, right? RTCA and DO160 and Milstan 810, all these have different specs on a rotorcraft experiences this GRMS level, so on and so forth. Fixed wing does this, and so on. But hang on a second. If those specs talk about rotorcraft and fixed wing as being two different things, right? Two different things. eVTOL is a weird combination of the two, right? So we really need to think about how, if we want to replicate a vibration environment that the eVTOL itself experiences, it's probably not as simple as it's either a fixed wing aircraft or it's a rotorcraft. It's some combination of the two. So let's go measure vibration in flight tests and use that to create shaker specs that are meaningful to your actual aircraft, which is an amalgam of rotorcraft and fixed wing behavior. Okay, that way we can make durability tests that really make sense. So this shaker rig here is shaking things in a way that the actual aircraft shakes them, and we have greater confidence in this durability validation test being correlatable to in-service loading. All right, last thing to look at here is reliability. Okay, so durability I like to think of as a structural problem, and Doug talked about this with torsional vibration and first bending mode and all this kind of stuff. Okay, terrible things can happen if we're not aware of those. We're going to move out of the structural side now and look at reliability instead, which is reliability is literally what's the probability that this thing can keep doing its thing to a certain amount of time, to 30,000 flight hours or something like that. Okay, so we're going to end up using this concept of reliability two different ways. One is when we're designing or developing a new product. So blank sheet of paper, we do an FMEA to say what are critical failure modes we ought to be aware of when we're designing an eVTOL aircraft. In the product development world, we're also going to use this thing called a fault tree diagram, right? And the fault tree diagram essentially is a way of trying to find those single points of failure that Mitch referred to earlier, right? We don't want to be surprised by these single points of failure. So we essentially break down the entire system into, here is a fault. Here's something that could happen. The brakes could shut down or whatever. Flight control could be lost or whatever it is. And then, so this is the effect up at the top. And then these are causes that filter on through. And this is a really simple fault tree diagram I've got here, just because we will try to keep things simple so you guys can actually see it on your screen. Realistically, an eVTOL subsystem, system, or entire aircraft could have hundreds or thousands or even tens of thousands of these little causes filtering all through. Okay, but this is a way then of being able to recognize where are those single points of failure. Where are those single points of failure? Okay, so this is going to be really, really, really important for us to recognize up front and use this as a tool to design reliability into our aircraft. Second way reliability comes into play is in fleet operations. So let's just say, skip ahead like 5, 10 years, whatever it is. Let's just say that your eVTOL aircraft are certified, they're flying. You've got a fleet of air taxis now. Okay, let's just say you make it that far. I hope we all do. Hope we all can. So we have hundreds of these air taxis flying around. That's great. Next question is, how do we keep that fleet moving? How do we keep that fleet alive? It really comes down to trying to answer the question of how do we keep that fleet available? And also, how do we address its maintainability? All right. So what we've got here, this is a reliability block diagram of a series of parts and how they interact together, and how time to failure or mean time to failure or reliability data for each component is cascaded or combined into reliability of the entire system. We have some pieces here that have redundancy built in. In other words, if this one fails, this one can continue to work. This is not a redundant part. If this fails, then this entire flow, this entire system shuts down. Okay. So if we can recognize how all these different systems fit together, or components fit into subsystems, into systems, how they all fit together, then we can start to think about how do we maximize the ability of this thing to keep doing that. In other words, our fleet to keep flying. We can think about maintainability and how do we schedule maintenance to maximize flight uptime and to minimize cost. So this might be a little ways out for you. If you're, in the design phase, you might be more over here trying to recognize where is risk. But at some point, when your fleet is flying, then we'll have to think about how do we keep that fleet flying in an optimal way. Okay, so with that in mind, let's just summarize here. Quickly. What we just looked at is really kind of the competitive, odd, tricky engineering landscape of the eVTOL world. Tons of promise, lots of open design space, but some challenges that came with it. Challenges like how do we maximize the performance of the electric powertrain, for example. Mitch talked about that. How do we manage noise and vibration, both from a structural certification and noise perspective, but also from a public acceptance perspective as well. That becomes really critical. And then I followed up here. That was Doug talking about that. And then I followed up here with strength and durability, lightweighting, and reliability as challenges. But so tricky environment we're in here. eVTOL world is new, exciting, kind of daunting at the same time, right? So some new challenges. Propellers have brought back some old challenges, but in spite of that, just remember HBK has a lot of solutions to these challenges. Okay. All right. HBK, we're not going to certify anything for you. We're not going to design stuff for you, but we've got tools that'll help with all this. We've got tools all along. I hope you've seen challenges, but also solutions as well today.
Thanks, everyone.
Thanks, guys.
Bye.
Cheers.
Bye.